Hello, Mr. Claudia here, and today we have our curve sketching lesson. We finally made it. We've spent the past 4 lessons learning all the basics of curve sketching, all the different components, and now we finally reached this point where we're going to be able to, by the end of this lesson, which is actually kind of a 2-day lesson, we're going to be able to take any function, do a bunch of things to it, and then be able to sketch it completely. And I put this picture here because it's a lot. Like these questions are typically about half an hour long, so we're probably only going to get to do one example, and then you'll have 1 or 2 to do for homework. What I've presented here on the front page is all of the kind of the algorithm or the method you're going to use to do this. So you just kind of follow this kind of these simple steps. So when we give you a curve, the first thing you're going to do is the stuff that we learned before this course. So find the domain. You're going to look at, try to use some clues from the function family, look for places where the function does not exist by setting the denominator equal to 0. Then you're going to find the intercepts. Remember, for the x-intercepts, you set the function equal to 0, or you set y equal to 0. To find the y-intercepts, you set x equal to 0, or you sub in x. Then you're going to find any asymptotes. Now, this is only where applicable. This is only for rational functions, functions that look like a fraction. You're going to have to find the vertical asymptotes by setting the denominator equal to 0, and then you're going to have to find the end behavior. Remember, we did a lesson on that where you sub in values that are very close. You have to find horizontal asymptotes. This one we tend to use the trick. So we look at the degree of the numerator and the degree of the denominator. If they're the same, then we look at the coefficients. If they're different, we either have no horizontal asymptote or we have a horizontal asymptote of 0. So remember the trick, and you also have to do the end behavior for that as well by subbing in large values. After that, we're going to analyze the first derivative. Now, if you remember the first 2 lessons of this chapter, the first derivative helps us know when the function is increasing or decreasing. Remember, we made a sign chart for the first derivative. And then using the critical points, we can, which is where the first derivative is equal to 0 or the first derivative does not exist, we can test those points using the first derivative test and see if they're relative maximum or relative minimum points. So you can figure out kind of the ups and downs and the little peaks and valleys as you go. Then we're going to find the second derivative test. The second derivative test, we do very similar things. So we find possible points of inflection, that's where the second derivative is equal to 0, it does not exist. Then by looking at the sign chart, we can decide which areas are concave up, which are shaped up like a cave facing up, or concave down, which are shaped like a cave facing down. And we can find the points of inflection. Remember, points of inflection are where the second derivative is 0 and there's a change in concavity. Now that you have all that information, you're just about ready to sketch. You just need to make sure you calculate your y values, because remember, we found the critical points, the max and min points, but we only found the x coordinates of them. So we have to sub in the x values into the original function to find the y values. We should draw the asymptotes, show kind of the, with broken lines. We should show the end behavior. We should plot all the points we know, the x, y intercepts, the max min points, the point of inflections. Yeah, we draw the end behavior, and then we kind of smoothly we connect all of those features to make the curve. So we have a long checklist of things to do. You can keep coming back to this. You'll find that there's kind of a repetition that we're going to get into as we do these questions. I mean, you're going to find the first derivative and do a bunch of things. Then you're going to do the same thing with the second derivative. So if you systematically work through everything, you'll find these are really neat questions. And the more you do, the more practice you get, the better. So this is usually a 2-day lesson. The first day, we're going to do polynomial functions. So functions like this have no asymptotes. So it's a little bit easier. We get to skip one of those steps. So we're going to do this example. And then, of course, you have a few for homework. So let's get started here. You need lots of paper today. So here we go. This is, 8.5, page 3. Here we go. So I'm going to do the example f of x is equal to x cubed minus 6x squared plus 9x. And you're thinking, what does this look like? Well, we're going to find out. Okay, let me go to my checklist and we'll do step one at a time. So the first step, determine the domain. Take lots of space here. Don't try to cram in your work. You're an artist with a blank canvas. This is polynomial function, so we know that there is no restriction on the domain. X belongs to all real numbers, so you know the function is going to go on forever to negative and positive infinity. The next thing I need are the intercepts. Okay, well the y-intercept, if you remember, I set x is equal to 0. So that means I have f at 0 is equal to 0 cubed minus 6 times 0 squared plus 9 times 0. So that is 0. Well, that's easy. So we know we have a y-intercept at 0, 0. So far, I'm really enjoying this, this curve sketching problem. We also need the x-intercept. To do that, we set the y equal to 0. So we have 0 is equal to x cubed minus 6x squared plus 9x. Now the only way to solve a higher order polynomial like this is to factor. Can I factor this? Well, it just so happens I can. This is not so bad. I can factor out an x and I'm left with x squared minus 6x plus 9. And then actually I can factor that trinomial. This would be x and x. What would make plus 3, or so minus 3 minus 3. So that means that the solution to this is x equals 0, and both of these are both x equals 3. So therefore, there's an x-intercept at 0, 0, and 3, 0. I mean, remember, it's x value is 3, the y value is 0. So those are my points. So already, I have an idea shaping how this function will look. Okay, now the next step would be to find some asymptotes, but there are no asymptotes because it's a polynomial. So I'm going to skip number 3, thankfully, and I'm going to go down to number 4. Number 4 is where I have to find the first derivative. So let's start by finding the derivative. So f prime at x is equal to 3x squared minus 12x plus 9. Okay, so now what do we do? Do we remember? Oh yeah, I have to find the critical points. So this should hopefully trigger your memory of what we were doing the past few days. Find the critical points and make a sign chart. So to find the critical points, by setting the derivative equal to 0. So I end up with 0 is equal to 3x squared minus 12x plus 9. Remember, you also would need to set the derivative or the denominator equal to 0, but in this case there is no denominator, so we just need to set the derivative equal to 0. I need to factor this now. Again, the only way to solve a quadratic is to factor it. So I'm going to factor out a 3, and then I need to factor this trinomial here. Let's see, so how do I get 3? Oh, that'd be minus 1 and minus 3. So I have a critical point at x equals 1, a critical point at x equals 3. What do I do with these numbers again? Oh, right. I need to figure out now if these are max or min points, and these can help tell me where the function is increasing or decreasing. So I'm going to go up here, and I'm going to make a sign chart. So this is the sign of the first derivative, and I have my critical values of 1, critical numbers of 1 and 3. So now I need to figure out is the derivative positive or negative in these different intervals. The easiest way to do this, and the most reliable, is to use the table. So let me make a table, 3 intervals, 2, so I have an interval here, x is less than 1, x is between 1 and 3, x is greater than 3. Oops, there we go. And then I have, okay, my factors are 3, x minus 1, x minus 3. Okay, let's do this. So let me sub in some values and figure this out. Well, first of all, 3, that's always going to be positive. Doesn't matter what I select. Okay, let's select a number less than 1. How about 0? That sounds good. If I sub 0 into this is negative and this is negative. If I sub a number between 1 and 3, say 2, this becomes positive, this is negative. If I sub a number greater than 3, which is say 5, I would get a positive number and a positive number. Counting the number of negative signs, remember if you have an even number of negative signs, it's a positive. This is odd, so it's negative and positive. So wow, we just got some really useful information. This is a positive, this is negative, and this is positive. So the first thing we found out, the original function, remember that's the thing we're trying to sketch, is increasing. X is less than 1 and x is greater than 3. And it's decreasing between 1 and 3. Not only that, not only do we know where it's increasing and decreasing, we also know, okay, so for this section it's increasing and then decreasing. And for this section it's decreasing and then increasing. So we know that this is a relative min and this is a relative max. I like using the number line to actually help me do that, right? Up, down, that's a relative max. So therefore, there is a relative min at, what was it, x equals 1, and a relative, no, sorry, the min is at 3, and the relative max at x is equal to 1. All right, great. Whew. Again, we're collecting all this information. The last big step we have to do is we have to find the second derivative and do the exact same sort of steps, but this time to look at concavity and points of inflection. So, again, taking lots of space. Don't try to cram your work in here because there's a lot. You want to take your time and not miss anything. So the second derivative of this function, well, I'm going to use the first derivative, take the derivative of that. So that gives me 6x minus 12. Look at how the function has gotten easier. Remember, we've seen that pattern where every time you take a derivative, you actually go down by 1 degree. So to find the, I don't call them, they're not called critical points, I call them possible POIs. And to do that, we set the second derivative equal to 0. So it's almost the same strategy as last time. We have 0 is equal to 6x minus 12. This you could factor, right? That's a great way to solve a question like this. So therefore, you know that x is equal to 2 is my possible POI. Now, just like before, I'm going to draw a Sine diagram. And we're going to look at what happens on either side of x equals 2. Now, you can use a table for this if you want. You might not need to, right? You could do it by inspection. If I sub in 0, what happens to this function over here? Well, it would be 0 minus 12, so it would be negative. If I sub in a number greater than 2, say 3, I'm going to get a positive number. It's up to you. I mean, I'm going to just do a quick table, but at this point, the table isn't always necessary because it's such a short question. But I like, the thing about the table is something you can do on autopilot. You don't actually have to think about it as much as other parts of the question. So this might be a good thing. If I'm just going to do a table because I know it's going to give me the information I need. So 6 is, but you have to have a factored version. So that's why you have to have this version of the question. So 6 is always positive. If I put a number less than 2, like 1, this is going to become negative. And if I put a number greater than 2, like 3, this can become positive. So this is negative, this is positive. So x equals 2 could be a POI. But the other thing, and this is a big point in IB, to know it's a point of inflection, the second derivative has to be 0, and concavity has to change sign. Well, it just so happens that concavity changes sign. We go from negative to positive. So this is some sort of point of inflection. And I'm just going to make my note here to say that therefore f at x is concave down for x is less than 2, and it's concave up for x is greater than 2. That's the information we learned from the sign chart with the negative and positive. And we've also learned that there is a POI, point of inflection, at x equals 2. Oh boy, can't see it. Okay, so now I've collected all my information. Now it's time to sketch. Remember on my checklist here, or algorithm, I have to sketch the curve, but first I need to calculate the corresponding y values. Like for example, I just found the POI at x equals 2. What's the y value for that? So again, I told you this is going to be a big question. We need another sheet of paper. Okay, let's do this. So right there. Okay, so this is, what is it? 8.5, page 4. Many more to come. So we're into step. I seem to have lost my page. Oh, right here. Okay. I have, we're on to step 6, which is sketch. But first of all, I need to find the coordinates, find the y coordinates. I'll find both coordinates of the max, min, and the POI. So if you remember, our minimum was, or maximum was at x equals 1. So I need to find the corresponding y value. So I'm going to sub in to my original expression, x equals 1. So I'm going to get 1 to the power of 3 minus 6 times 1 squared plus 9 times 1. That gives me 1 minus 6 plus 9, and that gives me 4. I'm just going to make a note here what I was doing. This was the local max point. Should I make a note here like that we're subbing into the original equation? Let me just say sub into original f at x equation. Because remember, that's what we're trying to graph. So that's why I want the y value from this function. So there it is, 4. Okay, my other point. Okay, so I need to do the local min, which happened at x equals 3. So I have 3 to the power of 3 minus 6 times 3 to the power of 2 plus 9 times 3. Sorry, I should show you what I'm doing here. The relative min was at x equals 3. So I'm subbing in x equals 3. And I am going to get 3 times 3 is 27 minus 6 times 3 times 3 is 9, which is 54. 9 times 3 is 27. Okay, so I have 27 plus 27, 54. 54 minus 54 is 0. That's pretty cool. And this actually was calculated before. We actually found this point, 3, 0. We found it to be one of the X-intercepts. So I actually could have skipped doing the math because I already knew that at x equals 3, the y value is 0. So as an X-intercept. So that's one thing to keep in mind. You might already know something about the points. Finally, the POI we know is that x equals 2. So I need to find the y value. So I'm going to sub 2 into my equation. 2 times 2 is 4 times 2 is 8 minus 24 plus 18. So I have 26 minus 24, which is 2. That's the POI. Okay, so now let's just kind of summarize it all over here. I have an X-intercept, 0, 0, and 3, 0. We calculated that before. I have a Y-intercept of 0, 0. I have a relative max at 1, 4, relative min at 3, 0, and I have a POI at 2, 2. That's kind of all the points that all the features we're gonna have to put in the sketch. So I'm gonna zoom out a little bit just so you can see a bit more. And now it's time to finally, after 2 pages of work, to finally sketch this curve. Fortunately, I don't have graph paper here. I mean, it is a sketch, so it's understandable that it's not perfectly the scale. The whole idea is that you're marking the important points and you're drawing the shape correctly. So, but I'll try to be as clear as I can here. So I want to go up to maybe 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Imagine this is the part of the video that you fast forward a bit. I don't need to see Mr. Quaddy make a Cartesian plane. Where he's labeling every point. Okay, alright, so let's start putting all these points on. So first of all, we have an X-intercept at 0, 0. We have another one at 3, 0. Great, we're off to the races. Okay, now we've got a local min at 1, 4. So there's a relative max, or it's right here at 1, 4. So you have to imagine, like, we know this is happening here. There's some sort of max point. We also have Y-intercept at 0, 0. So this is also the Y-intercept. Okay, the relative min is 3, 0. So we know this is a min point too. So we know actually the graph is doing something like that. And we also have a POI at 2, 2. So what did we find earlier? We found that the graph is increasing from less than 1 and greater than 3. So we know that less than 1, the graph is increasing. So from everything here, we know the graph's going up. We know that after 3, the graph is going up. We know between 1 and 3, it's decreasing, something like that. But of course, we know the graph isn't just straight lines like this. They curve. So does it curve like this, or does it curve like that? What's the concavity? Well, the curve was concave down for less than 2. So everything on this side should be opening downward. So if you kind of can start to sketch this, remember it has to be opening down. This part has to be going down, and then it has to go through this intercept. And then everything greater than 2, it's opening up, it's concave up. So that's where it has to kind of look like this. Oops. And there we have our curve. We've done it. We've drawn that function. A few notes about the curve. Let's just take a look. So it has the intercepts. We can see that it clearly goes through the intercepts. We can see the max and min points. It's clearly reaching a max, clearly reaching a min. We can see this entire thing is concave down. Be really careful. There is a tendency that once I've drawn this part, it's like, oh, I'm just going to make a nice flare out this way. I'm going to make the graph flare out this way. But that's not true. That would be a change in concavity. The graph stays tight. It stays like this and keeps going down forever. But you have to make sure that it's always concave down. It's always that cave looking down. Here, similarly, it doesn't flare out. It's always going to be concave up. And this point, you should see a clear bend, a clear flex or inflection from concave down to concave up. So there you have it. We've used our knowledge of calculus, all these skills we learned to sketch a curve. How exciting! You can check your answer using the graphing calculator, using Desmos. In fact, your homework tonight, you're always going to, for the first few, you're just going to use Desmos. Like, what do you need to look up? You just need to look up the final product. So I'm just going to graph this on our graphing calculator. I have x to the power of 3 minus 6x squared plus 9x. Enter. And there you go. Of course, the graph doesn't know to zoom in or zoom out, so I guess I should zoom out. zoom out. And you can see we get the same shape. So very nice. Oh, you guys can barely see that, but it's there. Okay. So I'm going to put this here. This is your homework then for tonight to do the, I've given you 4 more I'd like you to do. So again, they take a little bit of time each, but you need to get some practice and you need to see some other more tricky questions. I've given you more extra practices if you really want to do some more questions. There's a few. And then if you really want to see some neat math, remember that function, the curve of the probability normal distribution. Remember the normal distribution graph? Well, there it is right there. That's the equation I gave you when we did that lesson. See if you can graph it. And you're actually going to find that you can use the curve sketching strategy to graph that shape. So it's kind of neat. But again, these are the 4 that this is getting beyond us. Just try to focus on these 4. Okay, so now that you've finished your day 1 homework about the polynomial function and the curve sketching, let's go on to day 2. This is where we're going to do just one example, again, using our curve sketching algorithm, but this time we have a rational function, dun dun dun, which means that we need to do a little bit of extra work. We have to look at the asymptotes. So let's get started. So let's get a new sheet of paper. I'm going to put this off to the side. Again, I told you to have lots of paper, take lots of space, and here we go. We have another long question. So this is 8.5, page 5. Okay, so the function is f of x is equal to x squared over 1 minus x squared. Might as well, just before we go any further, I might as well just factor this, right? This is 1 plus x. 1 minus x is a difference of squares. Okay. All right, so my first step, let me just look back at my algorithm, is, oh yeah, determine the domain. Well, domain is a nice one. We know that because this is a rational function, there are places where the domain doesn't exist. There are x values that are not allowed. Those are the places where the denominator is equal to 0. So for to find the domain here, I'm going to set the denominator equal to 0. So I end up with 1 minus x squared is equal to 0. You know, I factored this, or I could have brought this to the other side. I get 1 is equal to x squared. I get x is equal to positive negative square root of 1. So I get x is equal to plus or minus 1. So therefore my domain is x cannot equal plus or minus 1, but otherwise x belongs to the real set of all real numbers. Okay, so hopefully you're imagining this graph. All is well with this graph except for 2 key spots. The second step is to find the intercepts. I'm going to try to cram them into this part of the page. First of all, I need to find the x-intercept. To do that, I have to set y equal to 0. So I end up with 0 is equal to x squared over 1 minus x squared. Now, this is where we have to rely on our training. How do I find the solution to this? Well, I can cross multiply, or in other words, I can multiply both top and bottom by 1 minus x squared. Now, that is just going to give me something times 0 is 0. So it just pretty much deletes the denominator, which is okay, because the denominator we're going to use in a lot of other sections of this question. So we end up with, okay, now the square root of 0 is 0. So the x-intercept is 0, 0. And similarly, we have to find the y-intercept. Hopefully you remember how to do this. This is where I set x equals 0. So I'm going to sub in 0 basically into that function. I end up with 0 squared over 1 minus 0 squared. So that gives me 0 over 1. That's okay. We can't have a divide by 0, but we can't have 0 divided by 1. That's just 0. So therefore, not only is 0, 0 the x-intercept, it's also the y-intercept. Still a little unclear about what this graph is going to look like, but at least I know something about the intercepts. Okay, let's keep going with our curve sketching algorithm. So we found the domain, we found the intercepts, now we have to find the asymptotes. And because this is a rational function, we can't skip this step. So let's start easy, let's start with the vertical asymptotes, set the denominator equal to 0. So for step 3, the vertical asymptote, I'm going to set denominator equal to 0. Now we've already done this too, right? We have 1 minus x squared is equal to 0. Oh, sorry, this should be denominator does not equal 0. These are the asymptotes, or this is the point where the domain does not exist. This time I'm basically going to find where the function is equal to 0. So I have 1 equals x squared. Same thing. I end up with x is equal to plus or minus 1. So those are my two vertical asymptotes. Therefore, VA at x equals 1 and x equals negative 1. Really important in IB that asymptotes always have x equals or y equals. You can't just say 1 or negative 1. You have to write them as equations because they are lines. Now, we all know that finding the asymptote is not the hard part. The hard part is this end behavior. That's the annoying part. Basically, for these vertical asymptotes, does the curve go up or does it go down? Now, to do this, let's start with x equals 1. You need to sub in numbers that are very, very, very close to x equals 1. Now, if you're approaching from the left, you're going to sub in a smaller number than this, so 0.99999. So let's take let's sub in 0.999. So I'm subbing that into my original function to see what happens. I'm going to use the factored form, which is up here. You can see it. So if I sub in 0.999, I get 0.999 squared, so that's positive. And that's over, okay, if I sub in 0.999 plus 1, that becomes also positive. And if I sub in 0.999 here, I have 1 minus 0.999, so I get a very, very small positive number. So with all that in consideration, I get a big positive number. So therefore, from the left, it goes to positive infinity. If you're unclear about this, take a look at that lesson we did on asymptotes. I'm going to speed up a little bit. If we're approaching from the right, I sub in a number just bigger than x equals 1. So that would be 1.001. Now we go back up here. This is going to become positive over positive. But 1 minus 1.00001 is a very small negative number. So I end up with a negative. So this goes towards negative infinity as we approach from the right. Now I also need to look at the other asymptote, x equals negative 1. Again, I'm going to approach from the left. If you imagine a number line, this is a number more negative than negative 1. So this would be sub in negative 1.0001. Something like that. Okay, I sub this in. I square it, so the numerator is actually always going to be positive. The denominator, okay, so I have negative 1 plus 1. That's still negative. And I have negative 1 minus negative 1, so that actually becomes positive. Confusingly enough. So this ends up being negative because I have an odd number of signs. So this is negative infinity. Finally, we have to do this one more time from the right. Thank God we don't have like 10 asymptotes. That'd be terrible. I'm going to sub in a number that's to the right of x equals minus 1. So that's going to be negative 0.999. Let's sub that in. The numerator is always positive because we're squaring it. Go back up here. 1 plus negative 0.9999 is still positive, a small number. And then 1 minus that number is, I'm going to be adding it actually, so it's going to become positive as well. So this is a positive sign, and this is heading toward positive infinity. Whew, end behavior. It's the worst, but at least now we know how the function behaves around these asymptotes. Sometimes for rational functions, you'll see that this is the hardest exercise of the question. Now we are not done. We also have to do the horizontal asymptote. This is where go through my tricks. And you could use limits, but a limit at infinity, but it's easier to use the tricks. Look at the degree of the denominator and the numerator. So in the original function, the numerator has a degree of 2, and the denominator also has a degree of 2. Remember the tricks. If the denominator, if the degree of the numerator is equal to the degree of the denominator, then the coefficient of the highest degree in the numerator divided by the coefficient of the highest degree in the denominator, that is the horizontal asymptote. So I'm going to make a quick note about that. Because degree of the numerator is equal to the degree of the denominator, therefore y is equal to, okay, so I got to take the coefficient of x squared here, which is just 1, and I have to take the coefficient of x squared in the denominator, which is -1. So I end up with 1 over -1, or just -1. So that is my horizontal asymptote. It's really easy if you use the trick. Now, of course, we know the hard part is actually to find the end behavior. And to make sure you're spelling behavior the correct way, right? There's a U in it because we're in Canada. To find the end behavior for the horizontal asymptotes, I have to sub in a really, really big number in the x direction. So f at, say, 1,000. And then do the same with the negative. So anyways, let's start here. So I'm going to sub in 1,000. So I get 1,000 squared over 1 minus 1,000 squared. Now it's going to be hard to do that in your head, but you can't really use a plus or minus situation like we did here, because we're looking at what happens at y equals -1. So you're either going to be slightly above -1, you're going to be at -0.99, so say that you come from above, or you're going to be slightly lower, -1.001. So the sign doesn't matter, the sign is going to be negative regardless. So I'm going to type into my calculator. Hopefully you can see this. Yes, 1,000 squared divided by bracket 1 minus 1,000 squared. And I get -1.000001. So that means that as you get very, very far along the x-axis, the y value of the function is -1.01. So it's just below this asymptote. So therefore, from below, y equals -1. Similarly, I have to sub in a really big negative number. So I'm going to sub in -1,000, and I get -1,000 squared divided by 1 minus basically the same thing. Therefore, it's also from below the asymptote. So now we have our asymptotes and we have our end behavior. That's the most, I find that to be the most strenuous part of this question. Whew, okay, let's get back to it. Where are we? Yes, we're going to sketch this curve. We still need the derivative, the first derivative, and all the things that come with it. Hopefully this will be like returning to a comfortable math skill that we've already learned. Number 4, I need the first derivative. Oh my god, the first derivative is going to require me to use the quotient rule. Such is life. So here we go. The derivative is the derivative of the first thing, which is x squared. So the derivative of that is 2x times the bottom thing, which is 1 minus x squared. Obviously, we're going to use this form because it's easier. This would require product rule and blah, blah, blah. So derivative of the first thing is 2x times the bottom thing, 1 minus x squared, minus x squared times the derivative of the bottom thing, which is -2x, all over the denominator squared. So 1 minus x squared squared. Okay, the calculus is done. Now all I need to do is clean up this, this answer here. Is there a common factor I can take out? 1 minus x squared, 1 minus x squared. There's no 1 minus x squared here. So remember, I do need to factor the top. I'm just going to expand first to see if I can clean it up. So 2x minus 2x cubed plus 2x cubed over 1 minus x squared squared. Be careful, you can't just distribute this and make it 1 minus x to the power 4, right? This square attaches to both of those, and to really get rid of it, you'd have to FOIL. You'd have to write this out twice in FOIL. But because it's already factored in the denominator, just leave it as is. Remember, all you want to do is factor this whole question. And we're pretty close here, actually. We have a minus 2x cubed plus 2x cubed. So we end up, those cancel each other out, and I'm left with 2x over 1 minus x squared squared, which is great because that's been factored. I can work with this. The next step, if you remember what we did yesterday, is I have to find the critical points. Now, I'm going to break my own rule here and try to cram this onto this page. To find the critical points, I'm going to do what I did yesterday. I'm going to set the derivative equal to 0. So I end up with 0 is equal to 2x over 1 minus x squared all squared. Now remember, when we solve questions like this, I'm multiplying both sides by 1 minus x squared all squared. So these cancel out, and then anything times 0, I basically get 0 is equal to 2x, or x is equal to 0. So when you set this rational function equal to 0, the denominator just kind of vanishes. So I found the critical points, but remember, the critical points can also happen when the denominator is equal to 0, when the function does not exist, or sorry, when the derivative does not exist. So I have to, I'll just put a little note there. Derivative does not exist. So that's another option to do that, and I put that in our notes here. Find the critical points where the function derivative equals 0 or the derivative does not exist. Well, the derivative does not exist when the denominator is equal to 0, so now I set 0 is equal to 1 minus x squared all squared. To solve this question, I need to take the square root of both sides. Square root of 0 is still 0. I'm going to bring x squared to the other side, and so x is the square root of both that plus, so it's plus or minus 1, because the square root of 1 is both plus 1 and negative 1. Remember, there are two answers. It all comes together. Okay, so now I know my critical points. And from my critical points, I can use a Sine diagram to find out some amazing things. So let's go up here. Let's write the sine of, let's make a Sine diagram for the first derivative. I'm going to draw a Sine diagram. So my points are 0, 1, and negative 1. So I have negative 1, 0, and 1. Now what I need to do is draw that that table so I can fill in the Sine diagram. Now this I'm going to have to really cram it in here because there's a lot to put on. But I have 1, 2, 3, 4 regions. So I have 1, 2, poor space management, but this is what you get. This is what I told us not to do, to try to take as much space as you need, but break my own rule. Okay, anyways. So we have a region, we have x is less than negative 1. We have x is between negative 1 and 0. We have x is between 0 and 1. And we have x is greater than 1. Okay, now what are my factors? Remember, that's why we did all this work. We need to get all the factors. So I had, okay, doesn't matter if the numerator, denominator, the way this works is you just write them all out. So 2x, and 1 minus x squared is all squared is one factor. And we're going to see how neat it is, how we'll be able to use that to figure this out. Okay, so let's take some test values. So what's a number that is less than negative 1? I think negative 2. Oh, wait a sec. This is always positive because 2 is always positive. Okay, where were we? Negative 2. Well, this would be negative. If I put negative 2 in here, it's negative 2 squared, which is 4. So I have 1 minus 4. That's negative 3, but then I square it, so it's positive. In fact, this will always be positive because of the square. So really what remains is to figure out this last row here. If I choose a number between -1 and 0, say -0.5, that's negative. Between 0 and 1, positive, and greater than 1, positive. Now I can count the number of negative signs. So this would be negative, negative, positive, positive. So now I can label my Sine diagram. Wow, how complex. So look at what I have. My function, the thing I'm trying to sketch, the thing I'm doing all this work for, it's decreasing when x is less than -1 and when x is between -1 and 0. It's increasing when x is between 0 and 1 and x is greater than 1. Whew. But also from this first derivative, we can figure out if there's a max or min. Remember, max or min happens if you change from negative to positive or positive to negative. So here it's decreasing, it's decreasing. Oh, but here it goes from down, decreasing, to increasing. So that is a relative min. And then here we go from plus to plus, nothing happens. So the other thing I should say, therefore, there is a relative min at x equals 0. Oh man, I'm just exhausted, but it's not over because I still have to find the second derivative to figure out the concavity. So let's continue with this question that never ends, lesson that never ends. We have 8.5, page 6. Okay, what are we doing now? Now I need to find that second derivative. So here we go. I'll just write out the first derivative again, just for memories. 2x, 1 minus x squared, it's all squared. Okay, let's find the second derivative. Man, the nightmare begins. So we have the derivative of the numerator, which is 2, times the denominator, 1 minus x squared, all squared, minus the numerator times the denominator. We know this is going to be bad, so let me put a square bracket. So something to the power of 2, well, that's going to be 2 times that something to the power of 1. And now the derivative of the something. So what's the derivative of the inside? That's a chain rule issue. That's negative 2x. And then that's all over 1 minus x squared squared, and then I have to square that whole thing. Whew, and then you give a big sigh of relief. We found the derivative, the second derivative. Now it's just a matter of cleaning it up and factoring it. First things first, look to see, do you see a common factor? I do. 1 minus x squared, 1 minus x squared, 1 minus x squared. I want to immediately get that out of the equation. I don't want it because I know it's going to cancel out. So let me factor out 1 minus x squared. I mean, I can also factor out an x. Nope. Oh, can I factor out? I guess I could factor out a 2 in the numerator, if it matters. So let's factor out a 2. I can do that later. The important thing is I want you to factor out the 1 minus x squared. And there's 2 of them here, a lot of them here, and 1 of them here. So I can only factor it out once. So then what's left in my numerator? Well, if I factor out a 2 and I factor out 1 minus x squared, I'm left with 1 minus x squared. If I factor out a 2 here, I'm left with, okay, 2 times 2 times 2. So I'm left with 2 times 2, which is 4. The negative and the negative become a positive. So it's going to be plus 4x squared, because the x times x. Now the 1 minus x squared, I just factored it out, so it's gone. Okay, so I think that's correct. I think I've probably skipped a step there. I could have done a little bit of ancillary cleanup. Now the denominator, I have 1 minus x squared all squared to the power. So these exponents actually I can multiply together. This one I am allowed to do because they're just brackets. So I end up with 1 minus x squared all to the power of 4. I'm just going to make a note of what I did there, which was factor the numerator. Okay, so now what's great is that, look, you have 1 minus x squared here, 1 minus x squared here. So I actually can cancel this out and with itself. And so there's going to be 3 left in the bottom and none left in the numerator. So I end up with 2, and I have that big square bracket, 1 minus x squared plus 4x squared. Do this right, 2, 4x squared, good, over 1 minus x squared to the power of 3. That's kind of the big thing that you have to do. You have to get rid of the common factor. Then it just becomes a kind of matter of cleaning this up a little bit. 1 minus x squared plus 4x squared. So I get 2 times 1 minus x squared plus 4x squared. I'm just going to dissolve that bracket. 1 minus x squared all cubed. So I end up with 1 plus 3x squared, because 4x squared minus 1x squared is 3x squared, over 1 minus x squared to the power of 3. Did I do that right? I think that looks correct. Again, the whole point of this is I want to get it into a factored form. Because I'm going to do a Sine diagram. But before I do a Sine diagram, I need to find the critical points. We don't call them critical points. We will call them the possible POIs. Similar to last time, to do that, I have to set the second derivative equal to 0. And even though it's scary, remember, if I do this, I cross multiply basically, and I end up with 0 equals 2 times 1 plus 3x squared. Basically, the denominator kind of falls away. And then to simplify this, well, I can divide both sides by 2, so I get 0 equals 1 plus 3x squared. I should bring the negative 1 to the other, or 1 to the other side, so I'm going to get negative 1 is equal to 3x squared. Divide both sides by 3, so I get negative 1/3 is equal to x squared. Can I take the square root of that? No, you can't take the square root of a negative number. So there's no solution here. This doesn't lead me anywhere. So again, there's no number you can put into this that will make this statement true. If you put in a negative number, positive number, this will always be positive, and you can't make it equal to 0. And when I solve the algebra, I get to this. This is where I really figure it out. Can't take the square root of a negative. That's okay. I also need to find where the second derivative does not exist. So that means I'm going to set the denominator equal to 0. So I have 0 is equal to 1 minus x squared to the power of 3. I'm going to take the cube root of both sides. So then I bring x squared to the other side. So that looks familiar. I get plus or minus 1. Oh, just getting really tired. Okay, so I should stop saying that. You guys are going to have to do a bunch of these for homework. Okay, so now I'm ready to make my Sine diagram. My Sine diagram of the second derivative. The hard part's kind of over. The nightmare's over. I've done that derivative. The possible critical points are 1 and negative 1. Now I will say at this point, and I think if you remember back from the lesson, it's unlikely that you're going to have a POI in IB. For IB's sake, it would happen when the derivative is equal to 0. It's very rare you get a situation where the second derivative doesn't exist and there's a POI. But we're going to do this for completion and just so you get an idea of what the whole thing looks like. Again, like, we're so deep in the mud right now, it's better just to follow a strategy we understand. And the strategy now is to fill in this Sine diagram. So I'm going to divide up my table. Okay, here we go. So I have x is less than, what was it, negative 1? Oops. X is between negative 1 and 1, and x is greater than 1. And then I have all my factors. So where was it? Oh, here. So I have 2, 1 plus 3x squared, 1 minus x squared, all cubed. Okay, let's look at some test values. Choose a number smaller than -1. -2. Oh, wait a sec. This is always going to be positive. Okay, -2. So I have -2 squared, which is 4, plus times 3 is 12, plus 1 is 13. So it's positive. Actually, this will always be positive, because even if I put a positive or a negative number, it's always going to be a positive plus 1. So I'm just left with this last one. Take -2. So -2 squared is 4. So I have 1 minus 4, which is -3. -3 to the power of 3 is going to be -27. It doesn't really matter the number. A negative number cubed is always negative. Interesting. What if I take a number between -1 and 0 and 1, say 0? Okay, I'm going to sub in 0 then. So I have 1 minus 0 is 1, cubed is positive. And if I take a number greater than 1, say 2, I have 1 minus 4, which is -3. Again, negative cubed is negative. Interesting. So I end up with a negative, positive, negative. Negative, positive. Oh, the old negative, positive, negative. So now, the whole point of this, well, I can find out, therefore, f of x is concave down when x is less than -1 and x is greater than 1. I can find its concave up when we go from between -1 and 1. Okay, what about the POIs? Well, I know what you're thinking. Hey, there probably should be a POI here, because look, I changed concavity, sir. It happens. You know, this is a possible POI point, and there's a change in concavity. We're all good. And you can think that, you could write it down, and it would be okay, but you would eventually figure out that, remember, -1 and 1, we've seen these points. These are scary points that have come up a bunch. These are the vertical asymptotes. So there cannot be a point of inflection at x equals 1 and x equals -1, because the function doesn't exist there. There is no point. So you would eventually realize that, but that's why I say in IB, the cases where you get the second derivative does not exist and a POI are rare cases with functions that we don't see in this course. So I'm just going to put a note there, because of the vertical asymptotes at x equals plus or minus 1, therefore no POIs. Okay, getting exciting now, because we have all the information we need now to sketch. And what you'll find with these kind of rational functions, most of the information we kind of have it. There's not going to be as much to kind of ancillary steps here. The X-Intercept. Where's my page? The X-Intercept was 0, 0. The Y-Intercept was 0, 0. So X-Intercept 0, 0. The Y-Intercept 0, 0. We had a vertical asymptote. X equals 1. X equals -1. We had a horizontal asymptote. Why did I underline it? Y is equal to -1. Okay, what about min and max? We had a relative min at 0. See, the y value of that, I already know it, right? I already figured out this point. There's a lot happening at 0, 0. There's a relative min at 0, 0, and we already said there's no POIs. So all the kind of key points, you already know them. It's just a matter now of doing the sketch. So I'm going to draw my curve here, or draw my Cartesian plane, or use some graph paper. And, oops. Okay, now technically we're really only looking at points 1 and -1, so I'm going to spread out my my axis a bit here, just so that I can sketch it really accurately. So this is 1, 2, 3, 1, 2, -1, -2, -1, -2. Okay, this is the fun part. I'm waiting for 30 minutes to get to this point. So first, the X-intercept and Y-intercept happens at 0, 0. So the only place where it goes through both axes is here. There is a vertical asymptote at x equals 1 and x equals -1. Draw these in a different color or as a dashed line or something like that. Okay. What else do we have? We have a relative min at 0, 0. So I know whatever happens, the curve's up here, it curves up here, right? Okay, and there's no POI. Let's sketch the end behavior. We spent so much time stressing about that. Let's see if we can figure it out. So from the left, so this is for x equals 1. From the left, it goes to positive infinity. From the right, it goes to negative infinity. So from the left, it goes to positive infinity, so it goes up like that. From the right, it goes to, so it's going down and getting closer and closer to negative infinity. Similarly, from the left, for x equals -1, from the left, it's negative infinity. From the right, positive infinity. So from the right, we said positive infinity. From the left, we said negative infinity. Okay. Oh, there's also the horizontal asymptote. That was at y equals -1. And what was the end behavior there? Well, we said that if you go in the positive x direction, it's approaching from below, and the negative x direction approaching from below. So you end up with like a shape like this. And over here, you go far over, it's below. Now you're basically ready to connect the dots. I know you might think at this point, don't I need more information? Well, you pretty much have it. Like, even if, look here, we know that the function's decreasing less than -1 and between -1 and 0. And we also know that it's concave down. Okay, so it's decreasing from up to -1, and we know it's concave down but less than -1. So it's cave that opens down like this. That. So I didn't do a great drawing there, but. And that's constantly going down. Then nothing happens at x equals -1. The function doesn't exist. And now it is decreasing, but it's concave up. Actually, this whole time it's concave up. So we actually have this curve. There's no points of inflection. It's just a parabola, basically. It's increasing now. And then between 1 and onward, greater than 1, it's increasing, but it's concave down. So I have a similar shape. And there it is. There's that function. Wow, what a weird function. You can see it's an advanced kind of rational function. Whew, and so there you have it. Through a lot of work, you're able to graph any function, including rational functions. So going back to our homework for today, remember the first part of this lesson, the first day you did these four. For the second part of this lesson, the homework today, you're going to graph these three rational functions. You can verify your answers with Desmos. I mean, that's really the name of the game. We want to see your final answer with the graphing calculator. And there's some extra questions if you really need some more practice. These do have some solutions in the textbook, so they're good in that sense. Good luck with those practice questions and all your curve sketching, and we will see you next time.